So yesterday, we finished the lecture with watching the video of manipulating individual atom at a very precise manner, right? So in that sense, after that, there were other tools kind of invented here. Previously, we were looking at this STM, scanning tunneling microscope. Working principle is basically electron tunneling, and we are going to actually talk about that in our a lecture later. Okay, so and after that other tools have been invented, and then one of them is a transmission electron microscope. Okay, so actually MPS has one as well. Okay, this TEM, the resolution is extremely small. Look at this one. This is a 0.2 nanometer. Okay, so in the sense, we can really resolve the individual atom with a transmission electron microscope as well. Okay, so for this one, this is actually images of a carbon nanotube. If you actually look at these images, I mean, it's probably a little bit hard to see, but do you see? There is kind of a two layers you can kind of see from this image. What that means is that there are two layers, okay, and in this carbon nanotube. Okay, so there are multiple types of kind of carbon nanotube. You can actually distinguish basically between single carbon nanotube and multi-wall carbon nanotubes. Okay, so obviously here all of them are multi-walls, but for this particular one, it has only two walls, right? So this one is actually quite small, and if you look at the dimension, this is only about 3 nanometers. Okay, so with this transmission electron microscope, you can really identify very, very small features. Okay, and then for this one, obviously there are more than 2 walls. You can actually identify how many number of walls this carbon nanotube has, and then even for this one, you can kind of apply this TEM to identify how many walls this carbon nanotube has. Okay, so this tool, I mean, it is very expensive. Okay, so this TEM, it can be easily $2 million. Okay, and actually the one we have at MPS, that one is I don't know exact figure, but it is more than $1 million. Okay, have you guys used a TEM here? No. Okay, yeah. So maybe I mean, at some point you might be able to kind of use it when you get a chance. And another more common electron microscope is a scanning electron microscope. Okay, so this one, in terms of resolution, is a little bit lower than TEM, but it still has a very high resolution. Okay, this one has about 10 nanometers. Okay, so and also with this SEM, you can actually get images of large features as well. Okay, so for example, if you look at this one, this is a flower pollen, and then this scale bar is 20 micrometers. Okay, so it's actually relatively big. So for this one, you can actually see, with the naked eye, but with this SEM, you can get just better resolution. Okay, and then this is snowflake. You can image also snowflake. This one is 1 millimeter. Okay, so obviously you can easily identify with the naked eye, but with the SEM, you can see kind of a small features, okay, of this, this snowflake. Okay, and then if you guys used the SEM before, you probably noticed this one is just black and white, right? Can you guess why?
Because it's not in the visible spectrum.
It's yeah.
The colors wider wavelength than the size of
Exactly. So basically, so the question actually comes from, which source do you use, right? So if you use optical microscope, the source you are using is essentially kind of visible light, right? And then with that, you can get a beautiful kind of the different color spectrums that we can see. But for this electron microscope, either this scanning electron microscope or transmission electron microscope, you are essentially irradiating electron, okay? Electron comes out from electron beam, okay? And then that one is kind of hitting the sample. For scanning electron microscope, you are essentially kind of collecting kind of a, like a bounced off electron from the feature, and then that is how you get the image. And then for transmission electron microscope, electron is transmitted through the sample, and then it's collecting the electron, and then depending on how it's kind of diffracted and like those features, you can actually recover these kind of like image features. Okay, so because of that, like you are just basically counting how many electrons arrive at the detector, right? So in the sense, you can only get just kind of gray images. Okay, so just white and black. Okay, so that is why you can only get just black and white images. But if you actually search for like literature images, you can find some color images of SEM. Those are essentially kind of post-processing. Okay, you are essentially kind of color coding of certain features, and that one is not really raw data. Okay. So this one is actually a very powerful tool, and probably if you have used it before, you probably also know how easy it is to operate, right? You just kind of be careful about hitting the sample on the beam, right? If you just avoid that, that one is fine. Okay. And another features that you can actually tell, this or the unique about these tools is that it requires vacuum. Okay, so optical microscope, you don't need a vacuum, right? But for this one, you absolutely need a vacuum. Okay, can you guess why? Yes.
The electrons will scatter if they're in open air, so that electron beam will be very diffused by the time it got to the
Exactly. So electrons is also kind of the kind of small object, right? But if there are many like like air molecules, it actually kind of bounce off from air molecules, and then you cannot really get high resolution. Okay, that is why like when you kind of learn how to operate SEM, you are asked to wait until vacuum reaches at a certain level, right? So obviously lower vacuum is better, but like that takes too long. So you just kind of wait until vacuum reaches a certain level, and then they will guarantee some level of resolution. Okay. So that one we will also cover that later. Okay, like how electron behaves and etc. And another kind of the topic I want to kind of touch on this introduction slide is the first human-made nanostructure. Okay, this one is called buckyball. Okay, this one kind of looks like a soccer ball. Okay, so it was created in 1985. Okay, by a scientist Richard Smalley, and then after this invention, he also got Nobel Award. Okay, and then the structure is essentially like all made of carbon atoms. Okay, the specific number actually is 60. Okay, and then this name is a nickname is a buckyball, and another scientific name is a C60. Okay, because a carbon atom, like a C stands for carbon, and then it has a 60 atoms in it. Okay, so C60, and in the shape of soccer ball, and then the diameter is only about 0.7 nanometers. Okay, so it's actually a very, very small, nanostructure that human made for the first time. And then this one is considered as a third form of a pure carbon. Okay, so first two are obviously graphite and diamond, but this third form is essentially man-made structure. Okay, so in the sense like scientists started making nanostructure by design and engineering. Okay, and since then nanotechnology really like widespread. Okay, so this is actually the data from 2009. These are essentially kind of how many papers were published in like various categories. Okay, so if you look at it, like all the nanotechnology related papers like basically spread it everywhere, right? I mean, for example, here if you look at it, materials obviously, and then chemistry, engineering, physics, computer science, and environmental, and then geoscience, ecological, agriculture, and biomedical, and health. Okay, so now, I mean, like I cannot really kind of find the data, but for now, I bet that this biomedical, like this stuff, should be much bigger than before. Okay, because think about it, even like like COVID vaccine, that is essentially nanotechnology enabled product, right? RNA. Okay. So in the sense, since then, I mean, nanotechnology enabled products basically spread it like even more. Okay. And also, this one is actually multidisciplinary in nature, because actually in order to kind of produce, or in order to manufacture the nanomaterials and characterize them, you actually need knowledge from basically like a different disciplinary area. Okay. So for example, if you actually, for example here, if you produce nanomaterial, okay, like let's say, you kind of found the recipe and then you characterize such that the nanoparticles are the size of that is ranging from, let's say, like 10 to 20 nanometers, okay? So then other researchers from different areas actually employ that recipe or use them materials to apply, their field, right? So in the sense, like for example, in this case, one paper was cited by, physics, computer, like chemistry, engineering, biomedical, cognitive. So if you actually kind of, introduce one critical idea that can make a significant impact on different areas, okay? So that is why, like in this mechanical engineering, we are also kind of teaching like these nanomaterials and like physics, and like quantum mechanics, okay? Because it kind of by nature, it contains multidisciplinary nature, okay? So, and as you, already know, like this nanotechnology is now currently used in various products, okay? So basically the idea is kind of simple, like it can create a lighter product and stronger product, and then it can create a faster kind of chip, faster, like a CPU, and then it can create a dense material or smaller kind of a structure, and then also it makes it more durable, okay? So if you look at actually number of products according to like several main categories, like most of them is actually allocated to this health and fitness. Okay, so this include the sporting goods, clothing, cosmetics, and sunscreen. And like if we actually go from kind of from right to left, some are automotive related, including tires and lacquers, and home and garden, cleaning supplies, and electronics and computers. This one is actually kind of now making huge impact, like including AI, right? How are we driving AI? Those are all thanks to, very high computing power and like, speed, right? And then goods for children and appliances, including like a washing machine and air cleaners, and also nanotechnology is used in food and beverage, okay? So for example, like a dietary supplement, okay? Or, like healthcare, that one is also, like kind of the vaccine and stuff like that. So, and then if you look at actually how this one has, like kind of spread it over time, if you look at this kind of category or the plot over time, like the blue is 2006, red is 2011, and green is 2013. Okay, so the most of them are in health and fitness, and then home and garden. Basically, over time, the nanotechnology enabled more products. Okay, introduce more products. And then if you look at just kind of health and fitness itself, okay, if we kind of create a subcategory, personal care, clothing, cosmetics, sporting goods, filtration, sunscreen, over time, the more products we're using nanotechnology, okay? And then, you may wonder, like also then, like what kind of materials have been used mostly, okay? And then this is essentially that kind of plot is showing, okay, so most nanomaterials is essentially kind of silver, okay? And then carbon, carbon nanotube, or graphene, titanium, silicon and silica, and zinc and gold. Okay? So, obviously as we saw, like we saw some silver nanoparticles and gold nanoparticles as examples, right, of changing optical properties as we scale down. Okay? And then those silver nanoparticles and gold nanoparticles, like are used in various applications. Okay? So these are actually kind of just some examples of nanotechnology consumer products. Okay, so if you look at like a tennis racket or even baseball bat, like it's many this like golf clubs, they kind of will say this has carbon nanotube or like a graphene and stuff like that, right? And then this is just kind of one example, like when you kind of embed the silicon nanoparticles in this, kind of sporting goods, you can actually increase strength and stability and power. Okay, so I mean currently many sporting goods introduce various kinds of nano materials, and they kind of advertise as better products, right? And another example is clay nanoparticles in the tennis ball. Okay, so like after you play tennis, like several sets, like now tennis ball is kind of squash, it loses the kind of bounciness, right? And then like they include these clay nanoparticles in the tennis ball, and then it tends to maintain pressure for long period of time. Okay. And another kind of example is actually gold nanoparticles in a pregnancy tester. Okay, so basically the way it works is that gold nanoparticles has kind of antibodies attached to the the gold nanoparticles, and then the pregnancy kind of a hormone, when it's like it's kind of when it detects, these antibodies kind of collect those hormone like the pregnancy hormones. And then because gold nanoparticles are so small, right, and then we can add actually a lot of them, okay, in this test. And then like now, since this one kind of collects antibody or hormone, pregnancy hormone, and then it can actually show the strong color contrast. Okay, so that is how these gold nanoparticles is used in the pregnancy tester. Okay, and also this kind of nano carnauba is used for like automotive industry. So this one is essentially kind of a coating on the car, and then because this one has kind of a nanostructures, so what that means is that when you have kind of scratches or like small pores in the car on the car surface, those nanomaterials can easily fill in, and also because of this kind of excellent mechanical properties, it makes kind of a very durable coating, okay, on them. So, and then this is another kind of example of clay nanoparticles. Okay, so like I mean now it's kind of hard to see like a plastic kind of beer bottles, because of environmental issue. But like you probably, I don't know if you guys remember, there were kind of a period where lots of beer like bottles made of plastic were introduced. Okay, and then the reason for that was because of actually nanomaterials. Like clay nanoparticles are kind of mixed in this plastic bottle, and then it actually contains the pressure, and then it doesn't lose the kind of gas as much. Okay, so that's how they kind of maintain freshness of the beer. Okay. And then obviously lastly this is nano transistors. So as they can make a smaller transistors, they can put more number of transistors in a given size. Okay, so what that means is that more computing power, right? So now current technology is about 3 or 4 nanometers. Okay, and then what that means is that like compared to like 10 years ago, now we are making like very small transistors, so we can actually add more number of transistors in a given size. Okay. So now actually another issue is that because we are adding so many number of transistors in the chip, the critical bottleneck is actually heat. Okay, because there are so many kind of working machine in the given size, and it's all producing heat, right? Because as we supply the current, and as long as there is a resistance, we have a Joule heating, right? Joule heating is I square R. Okay. And then that creates so much heat, given space. So like how effectively can we dissipate the heat? That is actually critical bottleneck. Okay, so and then regarding that, like many researchers or engineers are working on different ways of cooling. Okay, so So I'm not sure, like, if you guys have ever kind of assembled the computer, okay? If you kind of see the, heat sink for the CPU, do you guys have you guys seen the heat sink of the? That one is massive, right? I mean, CPU itself is very tiny, but heat sink itself is like this big, right? So that is because so much heat is released, and then you need that big heat sink to cool it down. Okay. So currently, like a kind of the CPU speed is capped at around like 5 gigahertz, like even smaller than that, and like there was a kind of the crazy experiment, like where people kind of pour liquid nitrogen on top of the like a CPU to kind of to maximize cooling, right? So then while you do that, I mean that is expensive experiment, right? And because you keep kind of basically like wasting the liquid nitrogen. But when you do that, you can actually push the frequency at like 7 gigahertz. Okay, so like if you actually introduce very good way of cooling, you can drive chip even faster. Okay, so basically like that is nanotechnology enabled products. And so then the next kind of question is how can we make these kind of nanostructures? Okay, so there are mainly two ways. Okay, so the first one is top down, and then the second approach is bottom up. Okay, so top down approach is essentially like we start with a kind of like a big chunk of material, and then we kind of cut down. Okay, so it's kind of like a machining process. Okay, you start with a kind of a big chunk of kind of material, and then you kind of cut it down, and then you make the way you want, right? And then the bottom up approach is like a kind of self-assembly. Okay, so basically, like you design materials or like molecules in such a way that these are aligned, kind of simple manner, okay, or self manner. Okay, so by doing that, you can create the structure the way you want. Okay, so like for these two approaches, obviously it really depends on like how which size of a nanostructure you want to make. Okay, so the top-down approach basically for nanotechnology is essentially relying on microfabrication process. Okay, this one is kind of like a machining process, but it kind of happens in like a smaller scale. Okay, so in the sense, this microfabrication process involves like photolithography and masking, etc. Okay, and then we'll cover that later. Okay, but for that one, obviously, if a feature size is larger and larger, it's actually simpler. Okay, it's much simpler. Okay, because you don't need to kind of create a smaller feature size. Like the tool that you need is much simpler, and it doesn't cost that much money. Okay, but if you want to make very small features, okay, like a 10 nanometer, 1 nanometer, obviously now this 1 nanometer with the microfabrication is kind of almost impossible. Okay, because current commercial technology is like 4 nanometer or 3 nanometers, right? So as you kind of make structures with a smaller size, the complexity and also the cost kind of is extremely high. Okay, but if you actually kind of take a bottom-up approach, this is kind of a self-organization or like most of like a live matter like work this way, right? So basically, like if you kind of work with just kind of simple DNA, okay, or like even smaller size kind of structure, from bottom-up approach is easier to do, okay? But with this bottom-up approach, like a kind of making, like this kind of like a mice is extremely difficult, right? I mean, the nature does that, but the human being, we cannot really produce, like a new, like a live matter, right? I mean, like this big size. So what that means is that, depending on which structure you are aiming for, you have to actually choose either bottom-up approach or top-down approach, okay? So that is essentially also kind of what many scientists work on. Okay, so if you want to make a, like, let's say 100 nanometer kind of size nanostructure, are we going to use top-down approach or bottom-up approach? Okay, so that is essentially, like and obviously, some scientists work on a bottom-up approach and some scientists work on top-down approach, and then both of them have merits and disadvantages. Okay. So in this course, I mean, we are not going to really talk about this bottom-up approach, but we will briefly talk about this top-down approach, okay, microfabrication process. Okay. So, and another way of thinking about this bottom-up approach is essentially kind of a 3D printer, right? So with a 3D printer, you can actually kind of like a bottom-up approach, but obviously we are not kind of talking about this scale, right? Like 3D printer, you are essentially using bottom-up approach, you are producing very bulk materials, okay? But in the sense, so actually some scientists also kind of use 3D printing to make a small scale, like a 100 nanometer kind of parts, okay? Obviously for that, you need to have a very small nozzle, like only dropping very small amount of quantity, okay? So, and then that is how they also produce some of nanostructures using, very small 3D printers. Okay. And also, I want to talk briefly about these building blocks for nanotechnology. Okay, so this one is essentially kind of like we are keeping in mind that these nanostructures will be scaled up. Okay, so in the sense, what are the building blocks? These are some examples. Okay, so the first example is nano clusters. Okay, so this is essentially nano cluster, and then typical size is less than 1 nanometer, and several atoms are configured such that it forms kind of the building block. Okay, and then the size is actually very small, less than 1 nanometer. And another type of building block is nanoparticles. Okay, so in this case, diameter ranges from 1 to 100 nanometers. And then in this nanoparticle, this is, by the way, this is a TEM image, okay, transmission electron microscopy image. And then do you see these individual dots? This individual dot represents individual atom, okay? And then this individual atom is essentially kind of packed together, forming nanoparticle, okay? And then diameter is just between 1 to 100 nanometers, okay? And then this is just a simple schematic of the nanoparticles, okay? So it's the individual atoms are packed together, forming nanoparticle. And then this one is a nanowire, okay, and then this one is a nanotube. Just difference is like whether it's a filled or hollow, okay. And then this nanowire, if you look at this scale bar, this is 100 nanometer. So in the sense, diameter is probably a little bit larger than 100 nanometer. For carbon nanotube, it's actually the diameter is less than typically 10 nanometers. Okay? And then these nanowires, nanotubes are up to like a millimeter long. Okay, so it's actually or even longer. So what that means is that this nanowire and nanotube, the aspect ratio is extremely high. Okay, think about it. This is like, let's say 10 nanometer, and then if we kind of assume that this is 1 millimeter long, aspect ratio is extremely high, right? So some researchers use these nanowires and nanotube as yarns, kind of for even producing kind of fabric, okay? Because its aspect ratio is pretty long, okay? So and then this is like tons of nanomaterials produced today. Okay, so this one is a specific example of carbon nanotube. So if you look at actually this top, this is a single wall carbon nanotube. What that means is that carbon nanotube has only one single wall. Okay, and then this one is a multi-wall carbon nanotube. So it has actually multiple walls. Okay, like more than just one wall. And then the production, capacity is, if you look at this kind of manufacturers, like USA, Japan, the production is only 65 or 10 grams per hour. Okay, it's actually very small quantity. So then you can tell, like in order to purchase the single wall carbon nanotube, you have to pay a lot more, right? And then for multi-wall carbon nanotube, actually, there are many manufacturers, basically, like located everywhere, Japan, Belgium, USA, and China, So if you look at actually the capacity is now kilogram, right? So, for single wall, it was a kind of gram level, but if for multiple carbon nanotube, they can produce, like tens of kilogram per hour. Okay, so in this one is actually much cheaper, but like if you want very high quality of carbon nanotube, you wanna basically go with the single wall carbon nanotube. So in the sense, like basically over time, the production level increases. Okay, so what that means is that like a more amount of carbon nanotubes are used in commercial products. Okay. Okay, so I mean this one is just kind of a the opportunity. This is essentially kind of stated in 2001. Okay, so a key challenge for nanotechnology development is the education and training of a new generation. The worldwide annual industry production is estimated to exceed $1 trillion in 10 to 15 years from now, which would require about 2 million nanotechnology workers. Okay, so this one was the kind of a statement given in 2001, and then in 2015, this the research firm basically studied and estimated that this nanotechnology enabled product generated $1.6 trillion in global revenues in 2014. Okay, so what that means is that this expectation was essentially kind of met, right? And then it has also kind of contributed to economic growth. Okay, and these are essentially different categories. So materials is actually like on the highest, and then electronics, pharmaceuticals, chemicals, like basically if you look at these categories, nanotechnology influences variety of kind of fields. Okay. So still nanotechnology is making impact, and that is why this course exists, right? I mean, we are essentially kind of educating and preparing for future generations. Okay. So basically, okay. So I mean, this one is kind of tied to this course goal. Okay. So like basically to take advantage of nanotechnology, or to utilize this nanotechnology, we first need to understand the science at nanoscale. Okay, so this is why we are going to focus on quantum mechanics quite a bit. Okay, and then with that, we will try to understand the fundamental properties of nanomaterials. Okay, so nanoparticles, nanotubes, nanowires, nanosheets, and we also need to understand how nanomaterials interact with one another and their surrounding environments. And by the way, these two items are essentially kind of tied together because, depending on the synthesis method and interactions, the nanomaterials property can drastically change. Okay, so because nanomaterials, are very sensitive to synthesis method, and also because of this high surface area, right, and it gets easily influenced by the interaction with the environment. Okay, so in the sense, I mean, this one is kind of challenge, like for consistent kind of production, but also this is also opportunity to tune the properties. Okay, so this is why nanomaterials kind of hard to what is it? I mean, still there is an issue that how we can maintain consistency. Okay, in production, and also the maintaining the properties. Okay. So then, once we kind of understand all this kind of a fundamental knowledge, and then we want to kind of apply that to engineer and design new devices and materials. Okay. So, we will kind of focus on this aspect in this course, and yeah, we'll see how it goes. And then this is a kind of typical technology trend, okay, for any like a new technologies. Okay, so first, over time, when the new technology is introduced, people are overly excited, okay, and then there is kind of exaggeration, and then people kind of realize, oh, this is actually crap, right? And then they kind of disappointed, and then but for those who remain in the field, they consistently develop the field, and then basically making some useful products, and they actually kind of start kind of satisfying consumers like that. Okay, so in the sense for nanotechnology, obviously when this one was introduced, definitely like it was kind of overly excitement was involved, and then people got disappointed. But I think we are still kind of in this realization stage. Okay, like for those who are working in nanotechnology, they are continuing to develop its own field. Okay, so and then this one also applies to, I think, crypto, right? The crypto thing, and then I think crypto also kind of first overly exaggerated, and then it went through some disappointment, and probably now it's going through maybe multiple bumps. Okay, so yeah, and then for AI, I don't know. I mean, it seems like it's very promising. I see the power. Okay, and then can we apply this one yeah, I guess we have to see how the path is gonna go. Okay, but anyway, so this is actually kind of general trend of all new technologies, and so my point here is that when people get overly excited, don't just go to that field, because you might actually end up at this a stage, right? I mean, another kind of example is kind of computer science, right? I mean, just about 4 or 5 years ago, computer science was a really hot major, right, in college. But now there is a news that computer science graduates are struggling to find jobs, right? I mean, yeah. So in the sense, I mean, this is a kind of a new technology. I mean, who knows which feature we are going to face? But yeah, I mean, yeah, just follow the passion, I guess. Yeah, and your path. Okay, so this is essentially kind of an introduction part, and we are gonna get into, let me see this, to the second slide. Okay, so by the way, yeah, I haven't posted this PowerPoint slide, but I'll upload this PowerPoint slide on Sakai, okay, along with the recorded lecture. So the next we are gonna discuss this scaling law, okay. Okay. So basically, in this topic, we are going to basically discuss if the size of a system changes by a factor, how do other quantities like force, volume, heat loss change? Okay. So in the sense, I mean, obviously, we are going to kind of try to downscale or upscale, okay, by a factor, and then we are going to see how that influences some phenomena. Okay. So, I mean, the reason why I'm introducing this is because, I mean, we are going to talk about quantum mechanics. Okay, so quantum mechanics is the governing principle for very small scale object or very small scale phenomena, like a small scale meaning like a nanoscale. But even at bulk scale, as we scale down or scale up, very interesting phenomena happen. Okay, but not quantum mechanics. Okay, we are still in classical mechanics regime, but we are going to see some interesting phenomena, okay, happening with scaling. Okay, so that is why I want to kind of introduce this before getting into quantum mechanics. Okay, so scaling laws describe how a physical parameter of an object or system changes in proportional to its characteristic length scale. Okay, so as we scale down and scale up, how our physical parameter changes. Okay, so and with that, interesting phenomena arise as the size of system changes, even before reaching the extremely small scale. Okay, so what I mean by that is, actually the next sentence here. As size shrinks to the nanoscale, the classical physics begins to break down. Okay, and then we have to really just focus on quantum mechanics. Okay, so a topic we'll discuss later. But here, interesting phenomena still happens even without talking about quantum mechanics. Okay, I mean later on it's probably it's gonna make sense, but we are gonna basically go over several examples. Okay. So this impact of size through scaling. Okay, so as the size of physical system changes, the relative influence of different forces changes. Okay, some become more dominant while others diminish depending on their nature. Okay, so we are going to talk about that in several examples. So changes in size determine which physical parameters will dominate system behavior. Okay, this concept is essentially scaling. Okay, so as we scale up, scale down, how physical parameters change. Okay, so in the sense, miniaturization, okay, just scaling down involves more than just reducing dimensions. Okay, so and then that is essentially because many systems do not scale linearly. Okay, so if your systems follow like just kind of linear, then it's going to be just kind of reducing dimensions. But some kind of scale exponentially or quadratically, and then because of that, there are actually different, kind of dominance of physical parameters. Okay, so some lose effectiveness when downsized, while others may become non-functional or physically unfeasible at smaller scales. Okay, so let's start with this kind of scaling in geometry. Okay, and I just want to emphasize again. We are not in quantum world yet, okay? We are still dealing with classical continuum mechanics, okay? So, and then just start with this perimeter area volume, okay? So obviously perimeter, as we scale up and down, is kind of linearly changing, okay? And then area is related to L square, right? The length square. And then volume is L cube, right? The length cube, okay? So I mean, this one we already know. I mean, this is again very simple kind of example. Let's start with that. Like we have this object. The width is L, and then we just kind of downscale by factor of 2. Okay, so what that means is that width is reduced by half, and height is reduced by half, and then third, this one is essentially like reduced by 1/8. Okay, from the original object. Okay, we are essentially kind of scaling down, right? By a factor of, in this case, 2, and then by a factor of 8. Okay, so then let's evaluate how the area changes, right? So in this case, obviously, like basically, the third this object, the area is 1/64, right? So this is just simple, and then this is essentially kind of how we are going to apply, okay, in this scaling law. Okay, so we are going to basically change the dimensions of the object by a factor of a certain number, and then we are going to see what kind of behaviors we are going to observe. Okay. So with that, let's kind of look at this kind of the several like animals. Okay. So look at this dog and hippo and elephant. Okay. So and then here, I want to look at the kind of a ratio of essentially the leg width to the body size, okay, or the total size. We are essentially kind of this kind of overstatement, but like we are kind of scaling up from here to larger and even larger, right? And then if you look at the actual kind of leg, compared to the body size, you probably can see that the leg width is much wider, right? So as we actually kind of scale up, this one is a 10 pound, 5,000 pound, and then 10,000 pound, and the width of the leg is getting wider and wider, right? It doesn't really linearly scale up. And that is essentially kind of my point. So, have you wondered why big animals have a very thick legs? So that one is essentially kind of we can actually use a simple kind of approach to analyze this. Okay, so for this imagine this is a kind of a simple model. Okay, this kind of plate is body now. Okay, and then the one leg one leg is kind of is representing this simple kind of circular beam. Okay, so then we are essentially kind of scaling down this object by a factor of like a certain number. Okay, we are essentially kind of scaling up and down. Okay, so if the system 1 is, let's say, 3 times larger than the system 2, okay, so we are essentially kind of scaling up and down. So h1, okay, the height, okay, 3 times, and then the width of the body is 3 times, and then the thickness, okay, d, is 3 times. Okay, we are essentially scaling up and down, right? So then the volume of 1 is essentially 27, right? Because like it's kind of cubic relationship, right? 27 times volume 2, and then the weight is essentially like in proportional to volume, right? Because weight is mass times gravity, and the mass is essentially density times volume, right? And the density is a kind of constant property, and then it has a volume in it. So volume is 27, and then weight is obviously 27 times, right? For when we compare system 1 with system 2. Okay. So then we have this 27 times larger kind of weight compared to the system 2. And then, imagine the pressure applied to this leg, okay? Pressure applied to this beam, okay? So in order to withstand this pressure, okay, pressure is essentially force divided by area. And then this force is essentially what? The weight, right? Weight. And then in order to withstand the same pressure, this area has to be 27 times difference, right? Yeah? Are you guys following here? Yeah. So in the sense, 27, but like let's say to support the same pressure, let's say, like we are essentially kind of evaluating how the diameter has to change to support the same pressure. Okay, so then area has to be 27, right, times larger than the column 2, and then we can evaluate the diameter now. Okay, so for this diameter is essentially like a square root 27. And then it turns out this is a 5.2, right? What that means is that, as we linearly scale up, it cannot really withstand the pressure, right? In order to withstand the same pressure, the diameter has to be greater than this factor, right? So this is why, like if you actually kind of look at this, as we scale up, in order to withstand the same pressure, the thickness has to be, larger than the factor itself. Okay, so in the sense, kind of funny picture here is like a King Kong, right? I mean, as we saw in the kind of movie, it's really linearly scaled up, right? And then if you actually kind of let's say if this kind of light matter exists, actually it may not even withstand its own weight. Okay, the leg itself is going to break, or leg has to be made of a very special material. Okay, so that is essentially kind of my point. Okay, so this scaling really makes kind of impact on several factors, and then we are going to go over several examples after this, but for today we are going to end here. Okay.